Welcome to Summarize Science, where we break down the latest research. Today, we're looking at a paper called Splat the Net, which introduces a groundbreaking new way to create ultra-realistic 3D scenes. For years, 3D graphics have faced a major trade-off. On one side, you have methods like neural radiance fields, or NeRFs, which use large neural networks to represent a scene. They produce incredible detail, but are very slow to render because they have to calculate every single ray of light, which is computationally expensive. On the other side, you have methods like 3D Gaussian Splatting, which are incredibly fast. Think of them as building a 3D model out of millions of tiny, semi-transparent blobs or primitives. This approach is fast because you can just project, or splat, these simple blobs onto your screen, but it's less expressive and often requires a massive number of them, which eats up memory. So, the big question has been, can we get the detail of a neural network with the speed of splatting? This paper's answer is a resounding yes, with a clever idea called splattable neural primitives. Instead of a simple, static blob, each primitive in their model is its own tiny, self-contained neural network. This smart primitive is spatially bounded by an ellipsoid, but within that space, the neural network can represent much more complex shapes and densities. The real genius is in the math. They design these neural primitives in such a way that they can be analytically integrated. That's a technical way of saying they can calculate exactly how it should look from any angle almost instantly, without the slow ray marching process. This means they can take these complex, neural-powered shapes and splat them onto the screen just as fast as the simpler methods. The results are pretty staggering. Here, you can see a scene rendered with traditional Gaussian primitives on the left and the new neural primitives on the right. The neural primitive version achieves a comparable, and even slightly better, quality score. But look at the numbers. It uses only 220,000 primitives compared to 1.5 million for the other method. That's almost 10 times fewer primitives, and the memory usage drops from 350 megabytes to just 84. This expressiveness is shown clearly here. To model this teapot, the neural primitives can intelligently deform to capture curved handles and sharp spouts with very few elements. The Gaussian primitives, being simpler, struggle to form these complex shapes and look much blurrier with a similar primitive count. When memory budgets are tight, the difference becomes even more stark. The models created with neural primitives retain far more detail and structure compared to 3DGS. Across various real-world scenes, their method consistently produces high-fidelity results that are on par with the best splatting techniques. So let's recap what this all means. The researchers have successfully bridged the gap between two major approaches in 3D rendering. They created a new fundamental building block for 3D scenes, a primitive that has the expressive power of a neural network but can be rendered with the efficiency of splatting. This results in 3D representations that are just as detailed and fast as the state-of-the-art, but are significantly more compact, requiring up to 10 times fewer primitives and 6 times less memory. What could this mean for the future? Imagine more realistic and complex virtual reality environments, real-time 3D product viewers online, or next-generation video games that can run on less powerful hardware, like your phone. By making high-fidelity 3D models so much more efficient, this work could accelerate the adoption of immersive 3D experiences everywhere. That's all for this episode of Summarize Science. Thanks for watching.